You have never in your entire life touched anything. Now wait. Before you dismiss that as crazy, think about it. You put your hand on a table, you feel it, solid, hard, right there. But here's the thing. The atoms in your hand and the atoms in that table never actually meet. They get close, sure, maybe a billionth of a meter apart. But then something pushes back, something invisible, something that fills the space between those atoms and says no further. That something is a field, and by the end of this talk, you're going to understand what that really means. Not just the word, not just a vague picture of arrows floating in space. You're going to understand what a field actually is, why physicists believe it's one of the most real things in the universe, and why this idea completely changed how we think about forces, matter, and the very fabric of reality. Let me start with something familiar. You've played with magnets, right? Everybody has. You hold two magnets, and you feel this invisible push or pull between them. No strings, no rubber bands, nothing you can see, just this force acting through empty space. Now, here's a question that bothered very smart people for centuries. How does magnet A know that magnet B is over there? How does the force get transmitted? Is there some kind of invisible substance filling the space between them? Or does the influence somehow travel instantaneously across the gap? For a long time, people just accepted it. They called it action at a distance. One object affects another across empty space, and that's that. Newton himself used this idea for gravity. The sun pulls on the earth pulls on the moon, and the force just acts instantly across millions of miles of nothing. But Newton was never happy about it. He wrote in a letter, and I'm paraphrasing here, that the idea of one body acting on another through a vacuum, without anything in between, was so absurd that no person with any sense of philosophical thinking could ever accept it. So if action at a distance is absurd, what's the alternative? The alternative is the field. Let me build this up carefully. Imagine you're standing in a room, and the room has a temperature. Not the same temperature everywhere, mind you. Over by the window, it's cold. By the heater, it's warm. In the corner, it's somewhere in between. At every point in that room, you could put a thermometer and read off a number. Temperature here, temperature there. Temperature everywhere. That's a field. A scalar field, mathematicians call it. At every point in space, there's a number. The temperature field fills the room. Now, imagine, instead of temperature, you're measuring something with a direction. Like wind. At every point in the room, there's not just a speed, but a direction. The air is moving. Here it blows left. There it blows up. Over there it swirls around. At every point, you have a little arrow, a vector, pointing in some direction with some strength. That's a vector field. And here's the key insight. The electric field and the magnetic field are exactly like this. At every point in space, everywhere in the universe, there is an electric field vector and a magnetic field vector. They might be zero in most places. They might be tiny, but they're there. The field exists at every point, whether or not there's anything there to feel it. Let me say that again because it's important. The field is not just a mathematical trick we invented to calculate forces. The field is really there. It's a physical thing. It carries energy. It carries momentum. It can push on objects. It can make things happen. The field is as real as the table you're not actually touching. Now, how did we come to believe this? Let me tell you a story. Back in the 1800s, there was a man named Michael Faraday. Faraday was a genius, one of the greatest experimentalists who ever lived. He discovered electromagnetic induction, the basis of every electric generator and transformer in the world. But here's the funny thing about Faraday. He had almost no formal mathematical education. He couldn't write down equations the way physicists do today. So he had to think in pictures. And the picture he invented was field lines. You've seen these. You sprinkle iron filings around a magnet, and they line up in these beautiful curved patterns radiating out from the poles. Faraday imagined these lines as real things, like invisible rubber bands stretching through space, pulling and pushing on charges and magnets. Now, we have to be careful here. The field lines themselves are not exactly real. They're a visualization tool, a way of drawing the field so you can see its direction and strength. The lines don't actually exist as little threads running through space. What's real is the field itself, the thing the lines are trying to show you. But Faraday's intuition that something real fills the space around magnets and charges, that intuition turned out to be profoundly correct. Then came James Clerk Maxwell. Maxwell was a mathematical genius, maybe the greatest physicist of the 19th century. And what Maxwell did was take Faraday's intuitive picture and turn it into precise mathematics. Maxwell wrote down 4 equations, just 4. And those 4 equations describe everything about electricity and magnetism, every phenomenon, every experiment, every motor, every radio, every beam of light. It's all contained in those 4 equations. But here's the miracle. When Maxwell combined his equations, he discovered something nobody expected. He found that the electric and magnetic fields could sustain each other, could create each other in a wave that travels through empty space. A changing electric field creates a magnetic field, a changing magnetic field creates an electric field, and this oscillating dance propagates outward at a very specific speed. Maxwell calculated that speed from known electrical and magnetic properties of empty space. He got about 300,000 kilometers per second, the speed of light. Do you see what happened? Maxwell had discovered that light is an electromagnetic wave. Light is nothing but ripples in the electric and magnetic fields. The very fields we use to push and pull charges are the same fields that bring us the sunshine, that let us see, that carry radio signals across the planet. That was one of the great unifications in the history of physics. Electricity, magnetism, and light, all the same thing. All manifestations of the electromagnetic field. Now let me pause and explain this in simpler terms. Imagine explaining this to a bright 12-year-old. Picture a pond. You throw a rock in, and ripples spread out across the water. The water has a disturbance at every point, a height, and that disturbance travels. The wave carries energy from where you threw the rock to the edges of the pond. The electromagnetic field is like the water. It fills all of space. When you wiggle a charge, you create a disturbance in the field. And that disturbance spreads out as a wave, carrying energy away from the charge. If that wave has the right frequency, we call it light. If it has a lower frequency, we call it radio waves. If it has a higher frequency, we call it X-rays or gamma rays. But it's all the same thing. Ripples in the electromagnetic field. Now here's where things get subtle. And this is the part that trips people up. What is the field made of? This seems like a reasonable question, right? Water waves are made of water. Sound waves are made of air. What are electromagnetic waves made of? For a long time, people thought there had to be something. They called it the luminiferous ether, a mysterious substance filling all of space through which light waves propagate, like an invisible jelly that permeates the entire universe. And they tried to find it. They did very clever experiments. The most famous was done by Michelson and Morley. They reasoned that if the Earth is moving through this ether, then light should travel at different speeds in different directions, like swimming with the current versus against the current. But when they did the experiment, very carefully, very precisely, they found nothing. No difference. Light traveled at the same speed in all directions, no matter how the Earth was moving. The ether didn't exist. This was a crisis. How can you have a wave without a medium? How can you have ripples without water? And the answer, the revolutionary answer that Einstein helped establish, is that the electromagnetic field doesn't need a medium. The field is its own thing. It's not made of anything more fundamental. It just exists. This is hard to accept. Our everyday experience tells us that disturbances need something to disturb. But nature doesn't care about our everyday experience. The electromagnetic field is a fundamental entity. It exists at every point in space. It can carry energy and momentum, and it doesn't need any underlying substance to support it. The field itself is the medium, or rather, there is no medium. There's just the field. Let me give you another way to think about this. Forget the word medium entirely. Think instead about what we can measure. We can measure the force on a charged particle at any point in space. We can measure the energy stored in a region of space where there's a field. We can measure the momentum carried by a beam of light. These are real, measurable physical quantities. Whether or not there's some invisible jelly underlying it all, that's a question that doesn't have any measurable consequences. And if it doesn't have measurable consequences, maybe it's not a meaningful question. The field is what we measure. The field is what's real. Now, let me address a common misconception. People sometimes think that electric field lines are like strings or threads that pull on charges. They imagine that when a charge feels a force, it's because it's being tugged by these lines. That's not quite right. The field lines are just a way of drawing the field. The actual physics is local. The charge feels a force because of the field at its location, right there, at that point in space. The charge doesn't know about field lines far away. It only responds to what's happening right where it is. This is one of the beautiful things about field theory. Everything is local. The field at one point affects the field at neighboring points. The disturbance propagates step by step. There's no mysterious action at a distance. Every cause and effect happens right next door. Now wait. Let me make sure you appreciate how strange and wonderful this is. Before the field idea, people thought forces acted instantaneously at a distance. If I moved a charge here, every other charge in the universe would instantly feel a different force. The effect would be immediate, no matter how far away. But that's crazy. If I wiggle a charge here on Earth, and some alien light years away instantly feels a different force, then information would be traveling faster than light. In fact, it would be traveling infinitely fast. The field theory says something different. It says when I wiggle a charge here, the effect doesn't travel instantly. It propagates outward at the speed of light. The disturbance spreads through the field like ripples on a pond, and it takes time, real time. An alien 10 light years away won't feel the effect of my wiggling for 10 years. That's how long it takes the electromagnetic ripple to get there. Let me walk you through a thought experiment. This is the kind of thing I love to do. Take a simple situation and really think it through. Imagine two charged particles, let's call them A and B, sitting in empty space, far apart. They've been sitting there motionless for a long, long time. Each one feels a force toward the other if they're oppositely charged, or away from the other if they're the same charge. And the field everywhere is nice and steady. It's had time to settle down into the static configuration. Now suppose I suddenly grab particle A and shake it. I move it back and forth. What happens? At the instant I shake, a particle B is far away. Does B instantly feel the shake? Does the force on B instantly change? No, it doesn't. Not even a little. Here's what happens instead. When I shake A, the electric field right near A gets disturbed. That disturbance spreads outward. It travels at the speed of light. It expands like a sphere, getting bigger and bigger. Meanwhile, particle B, way over there, sits in the old, undisturbed field. The force on B is exactly the same as before. Only when the expanding disturbance reaches B does B notice anything different. The disturbance washes over B, the field at B changes, and now B feels a different force. Now B responds to my shaking. This is not instantaneous. It takes time. The time it takes for light to travel from A to B. And here's something even more wonderful. That spreading disturbance, that ripple in the electromagnetic field, that's light, or radio waves, or whatever you want to call it depending on the frequency. When I shake a charge, I create electromagnetic radiation. I'm literally making light. This is how antennas work. In a radio transmitter, electrons in the antenna get shaken back and forth by an alternating current. This shaking creates electromagnetic waves that spread out at the speed of light. And far away, another antenna has its electrons shaken by the incoming wave, producing a tiny current that your radio amplifies into sound. The whole thing is just charges shaking other charges through the intermediary of the electromagnetic field. The field is the messenger. The field carries the energy and information from one place to another. Now let me get slightly mathematical, but I promise to keep it gentle. The strength of the electric field at a point is simply the force that a small positive charge would feel if you put it there, divided by the amount of charge. We write it as E. Big E for the electric field. So if there's a charge Q sitting somewhere, it creates an electric field that spreads out in all directions. The field is stronger close to the charge and weaker far away. In fact, it falls off as the square of the distance. Double the distance, the field is 4 times weaker. Why the square of the distance? Imagine the field spreading out in all directions like an expanding sphere. The same amount of field has to cover a bigger area as you get farther from the source. And the area of a sphere goes as the square of the radius. So the field, spread over more area, becomes weaker by that square factor. Same thing happens with gravity, same thing happens with light intensity. The inverse square law pops up everywhere in physics because of this simple geometric fact about spreading in 3 dimensions. The magnetic field is similar, but it's created by moving charges, by currents, and it has a slightly different geometry. Magnetic field lines wrap around a current-carrying wire in circles, but the basic idea is the same. There's a field vector at every point in space, and that field exerts forces on other currents and moving charges. Now here's where it gets really interesting. Electric fields and magnetic fields are not independent. They're connected. They're really 2 aspects of one unified thing. Maxwell's equations tell us that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. They're linked together in this beautiful dance. This is why electromagnetic waves can propagate through empty space. The changing electric field makes a magnetic field. The changing magnetic field makes an electric field. And the whole oscillating pattern travels forward at the speed of light. Let me paint a picture of what an electromagnetic wave looks like. Imagine a wave traveling through space to the right. At each point along the wave, there's an electric field vector pointing, say, up and down. And there's a magnetic field vector pointing sideways, perpendicular to the electric field. And both of them are perpendicular to the direction the wave is traveling. As the wave passes a point, the electric field there oscillates up and down. The magnetic field oscillates side to side. The whole thing marches forward, rippling through space, carrying energy from the source to wherever the wave is going. And here's something profound. The wave doesn't need any matter to travel through. It doesn't need air. It doesn't need water. It doesn't need the fictional ether. It travels through pure vacuum just fine. The electric field makes the magnetic field, makes the electric field, makes the magnetic field, all the way across empty space, from the sun to your eye, from a distant galaxy to a telescope. The field is its own thing. It sustains itself. It carries energy through the void. Let me tell you why this matters so deeply. Before the field concept, the universe was made of particles, little billiard balls bouncing around. Forces between them were mysterious and instantaneous. The picture was mechanical, like clockwork. After the field concept, the universe is made of particles and fields, and maybe, at some deeper level, just fields. The particles might themselves be localized disturbances in fields, little knots or excitations. This is actually how modern physics works. In quantum field theory, which is our best description of fundamental physics, everything is a field. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. The quarks, the neutrinos, the Higgs boson, all of them are ripples in their respective fields that fill all of space. The field has gone from a useful mathematical tool to the fundamental ontology of physics. Fields are what the universe is made of. Now, I have to be careful here. Quantum field theory is a deep subject, and I don't want to mislead you. The quantum field is not quite like the classical electromagnetic field I've been describing. It has quantum properties. It comes in discrete packets. The famous wave-particle duality is baked into it. But the essential insight remains. Physical reality is not made of little balls acting at a distance. Physical reality is made of fields filling space, interacting locally, propagating disturbances at finite speed. Let me give you one more way to appreciate how real the field is. The field carries energy. If I have a region of space where there's a strong electric or magnetic field, that region contains energy, real energy. Energy I could in principle extract and use. How much energy? It turns out the energy density, the energy per unit volume, depends on the square of the field strength. Stronger field, more energy. The exact formula involves some constants I won't bore you with. But the point is that empty space with a field in it has more energy than empty space without a field. This is not metaphorical. The energy is really there. In fact, this is how radio waves carry energy from a transmitter to a receiver. The oscillating electromagnetic field contains energy. That energy flows through space at the speed of light. When it reaches your antenna, some of that energy gets absorbed, heating up the electrons, creating the signal your radio picks up. The field carries momentum, too. Light can push on things. When sunlight hits a surface, it exerts a tiny pressure. This is called radiation pressure. It's small, but it's measurable. Spacecraft can use solar sails that catch sunlight and get pushed by it. How can empty space push on something? Because the electromagnetic field has momentum. The field is not just numbers at points in space. It's a physical entity with energy and momentum. It can do work. It can exert forces. A thing that has energy and momentum is as real as anything gets. Now let me circle back to something I hinted at earlier. What about gravity? Newton described gravity as action at a distance. The sun pulls on the earth right now with no delay. But if light takes 8 minutes to travel from the sun to the earth, shouldn't gravity take time too? Yes, it should. And it does. Einstein's general theory of relativity describes gravity not as a force acting at a distance, but as a field that is the curvature of space-time itself. Masses warp the geometry of space and time around them. Other objects move through this warped geometry, and that's what we perceive as gravity. And disturbances in this gravitational field propagate at the speed of light. We call them gravitational waves. They were predicted by Einstein and detected for the first time in 2015 by LIGO. When two massive black holes spiral into each other, they shake space-time. They create ripples in the gravitational field. Those ripples spread out at light speed, and if they reach us, they slightly stretch and squeeze our detectors, and we can measure them. So gravity, like electromagnetism, is a field theory. The field is what's real. The field propagates at finite speed. Action at a distance is an illusion, an approximation that works when things are moving slowly and far apart. Now wait, let me make sure I'm not oversimplifying. There are mysteries here, deep mysteries. In quantum mechanics, there's something called entanglement. Two particles can be connected in such a way that measuring one instantly affects what you know about the other, no matter how far apart they are. Einstein called this spooky action at a distance. He didn't like it. Does this violate what I've been saying? Does entanglement bring back instantaneous action? No, not quite. Here's the subtle part. Entanglement doesn't let you send information faster than light. You can't use it to communicate instantaneously. The correlations are there, but they only become apparent when you compare measurements, and comparing measurements requires sending information at the speed of light or slower. So the spirit of field theory is preserved. No information travels faster than light. Causes precede effects. The universe unfolds locally, step by step, neighbor affecting neighbor. But the quantum world is strange. There are correlations that seem to connect distant points in ways we don't fully understand. The field picture, even the quantum field picture, may not be the final word. We're still learning. Let me pull back and think about what this all means. We started with a simple question. How does one object affect another across empty space? The ancient answer was action at a distance, and it never really satisfied anybody. The field answer is different. The field answer says there's no empty space. What looks like emptiness is actually filled with fields. The electromagnetic field is everywhere. The gravitational field is everywhere. Various other fields are everywhere. And these fields are the medium through which influences propagate. But unlike the old ether, these fields are not made of anything else. They are fundamental. They are the bedrock of reality. Particles are excitations in fields. Forces are interactions between fields. The whole universe is a symphony of fields oscillating, propagating, interacting, creating all the phenomena we observe. This is a profound shift in how we picture the world. Not billiard balls bouncing in empty space, but fields filling space, rippling, vibrating, alive with energy and momentum. And here's the beautiful part. This picture is not just philosophically satisfying. It works. It makes precise quantitative predictions. Quantum electrodynamics, the quantum theory of the electromagnetic field, is the most precisely tested theory in all of science. Its predictions match experiments to 10 decimal places. No other theory in any field of science comes close to that accuracy. The field is not just a metaphor. It's not just a mathematical convenience. It's the deep truth about how nature works. I want to leave you with one final thought. You're sitting there, wherever you are, surrounded by fields. Right now, electromagnetic fields are passing through your body. Radio waves, cell phone signals, the light from the screen or the sky, the heat radiating from your own skin, the static electric field between your feet and the floor. You're immersed in a sea of fields. You're swimming in it, and you can't even see it. Most of what happens in physics happens in the fields. The particles, the matter, the stuff you can see and touch, that's almost like debris floating on the surface. The real action is in the fields beneath. When you understand this, when you really get it, the world looks different. Empty space isn't empty. Vacuum isn't nothing. The void is pregnant with fields, ready to ripple, ready to carry light from a distant star to your eye, ready to convey the shake of an electron in a transmitter to your radio, ready to bend around a massive planet and focus light like a lens. The field is what's really there. So next time you hold two magnets and feel that mysterious push or pull, remember what you're feeling. You're feeling the electromagnetic field. It's real. It's between them. And it's everywhere else, too. That's what a field really is. Not just arrows on a diagram. Not just numbers in an equation. A real, physical thing, filling all of space, carrying energy and momentum, making the universe work. I'd love to know what puzzles you most about fields. What question am I leaving unanswered? Shout it out or write it down. I'm curious what you're thinking.